Hi, and welcome to you. I am Anthony from LMMP PUC-Rio, and I hope you will enjoy the discussion about how to simply and quickly characterize solid-like films at oil-water interfaces with pen and drop tensiometer. Before getting right to the point, let's have a look on complex interfaces. One of our PhD students is working with water droplet immersion, and she observed that adding an anionic surfactant can prevent the coalescence. Depending on the concentration, a membrane will form at the interface. This phenomenon can easily be observed by oscillating the drop. Wrinkles appear, and it is possible to break this membrane with a sharp increase of the area. Main question here: what are the properties of this membrane? When does it appear? And can we get a better understanding of the skin formation dynamic? There are several possibilities to characterize these interfaces. Working with interfacial rheology by using a tool at the oil-water interface. It can be a double O-ring, a junior ring, or bicone. In this case, the size of the interface remains the same. The other way is to change the size of the interface by increasing and decreasing the surface area of the interface. This can be done with a alignment trough and also with oscillation of a droplet. In this presentation, we'll focus on the drop check technique. Drop tensiometer is a well-known technique. The shape of the drop depends on the balance between the interfacial tension and the gravity. The Young-Laplace equation allows to predict the interfacial tension just by knowing the density difference between the two faces and the contour of the drop. But some conditions needs to be respected for correct evaluation of interfacial tension. Firstly, the profile of the drop needs to be purely Laplacian. Secondly, the drop shapes need to be pair-like. This can be checked with the bond number, which gives information about the shape of the drop as a function of the volume and the interfacial tension. Usually, this number needs to be higher than 0.1 to avoid any artifact measurements. And finally, the drop must be axis symmetric for the outline evaluation. Interfacial tension is really interesting because it gives information of dynamic absorption of the surfactant at the interface, but it doesn't allow to get information about the rheological properties of this interface. To access the rheological properties of the interface, we need to oscillate its area. Surface stress resulting from small area variation can be expressed as the sum of an elastic term and a viscous term. The elastic modulus, E prime, stands for the impact of the change area on the surfactant concentration change at the interface. The viscous modulus, E prime prime, describes the time dependency due to equilibration between the bulk and the interface. So, depending on the bulk concentration, the surfactant properties, the oscillation parameters, this moduli will change and give a mapping of the rheological properties of the interface. However, describing the behavior at the interface by considering only the interfacial tension is not sufficient, as shown by Jensen and Verment, because it also depends on an extra stress at the interface. For complex interfaces, the extra stress tensor can have significant deviatory contribution to the interfacial stress since the drop doesn't deform homogeneously. A consequence is that large errors start to be observed when fitting the Young-Laplace equation. So this tool is then incomplete to describe solid-like interfaces. And if we want to measure rheological properties, we need to follow some limitation for the measurement. In addition to not being spherical, the oscillation frequency needs to be lower than 1 Hz, and the amplitude of deformation doesn't exceed 10%. It is also important to avoid the appearance of wrinkles for an accurate area measurement. It is possible to avoid all this limitation. In recent years, several groups have worked on extending dynamic surface tension to include additional stress contribution, taking into account the contour of the drop. But these methods are complex. They require post-processing and are time-consuming. So our issue here is quite simple. How to simply and quickly characterize the transition from a simple to solid-like interface without using the Young-Laplace model. When we oscillated the drops, we observed that the shape evolution depends on the interface properties. Let's take two examples. On the left, we see that this drop is quite spherical, and it keeps its shape whatever the volume is. This is a simple droplet of oil in contact with water without any species at the interface. On the right, a skin is already formed at the interface. When the volume started to decrease, the drop changed from a spherical to a pear shape. The drop stretched, then stabilized. Its length no longer changed while its radius decreased. So we can therefore easily conclude that the pattern of the shape of the drop depends on the properties of the interface. As the evolution of the volume and the area is not the same with the deformation, we decided to evaluate the volume-area ratio. For a drop of oil immersed in pure water, it will expand as a sphere. Therefore, a perfect sphere should show a ratio about 1.5. If the interface looks like more a solid, the shape of the drop will no longer be Laplacian. As the volume decreases, the drop looks more like a cylinder than a sphere. As interfacial tension decreases significantly, drop doesn't change length during the oscillation, and this ratio will be about 2. So, this increase of the value of the ratio reflects well the deviation of the drop shape from purely Laplacian. It is then possible to identify with a simple parameter the changes in rheological properties without measuring interfacial tension. To prove the concept, we work with a sunflower oil droplet in contact with a water phase. We formed the drop, waited for the equilibrium for the interfacial tension, and then started to decrease the volume of the drop. At the beginning, the bond number is higher than 0.1. The interfacial tension remains constant and doesn't depend on the surface area. The R ratio is between 1.41 and 1.42. As the volume keeps decreasing, we reach bond number values lower than 0.1, and the interfacial tension starts decreasing. The accuracy of interfacial tension is strongly dependent on the shape of the drop, as a spherical droplet is out of Laplacian profile, so it is normal that there is a deviation of interfacial tension. But here, the R ratio is not affected by this transition. The values of the R ratio change only when the drop is very small and its shape approaches a sphere, and therefore the theoretical value of 1.5. The bond number is then a parameter related to the first slight deviation of the contour of the drop. Then the R ratio gives an additional information for small spherical droplets when the deviation of the interfacial tension is strongly important. Let's see now the case of a complex interface. We did the same measurement that before, waited for the equilibrium at the interface, and slowly decrease the volume of the drop to avoid any additional stress on the interface. The initial value of the R parameter is about 1.7, quite larger than the 1.41 value for spherical droplet without membrane at the interface. When we start decreasing the volume, this number goes from 1.7 to 2. This is because the shape of the drop is going from a sphere to a pear. After this point, the area and the volume remain constant, and after point 3, roughness begins to appear on the surface of the drop. This is characterized by a decrease of the R parameter, while interfacial tension is not affected. No slope breakup, because in this case, the outline of the drop remains the same, so it's quite impossible to notice this change with the interfacial tension. The standard deviation from the Laplacian profile helps to get a better idea of this deviation, because it has the same trend than the R parameter. After stage number 3, we start losing the axisymmetric profile of the drop, and the software cannot measure the local area variation of the interface. We identify two different zones. This one, far from the Laplacian profile for the interfacial tension, but also complicated to estimate the R parameter because there is a deviation of the area of the droplet. And this one, this green one, where we have a deviation of the interfacial tension, but we can measure the evolution of the R parameter to estimate this deviation. We demonstrated that these concepts work well for extreme cases, spherical droplet and complex interface. So the question is now to use this parameter to identify the dynamic transition of the interface. For the evolution of the interface transition with time, we made a drop of water in contact with a two-weight person span 80 in oil and started periodical oscillation from time 0 to 1 hour. The amplitude was set at 10% and the frequency at 0.1 Hz to avoid any additional stress at the interface. Here I'm going to compare the elastic and viscous moduli to the volume area ratio. I divided this graph into 3 different parts. The first one corresponds to the first dynamic absorption of surfactant at the interface. As the dynamic is quite important, measurement of oscillation can be affected, but it seems that the 3 parameters are quite constant. The second zone corresponds to the organization of the surfactants at the interface to make the structure. Slightly appears at the interface, the viscous modulus decreases while the elastic modulus increases. Little by little, the structure avoids the transfer between the bulk and the interface. This appearance leads to an increase of the volume-water ratio from 1.35 to 1.6. This zone ends with a maximum of the elastic modulus, while the viscous modulus is quasi equal to 0. At this point, we could think that the structure at the interface is almost complete. But after this time, the elastic modulus started to decrease, whereas the R parameter keeps slightly increasing. We could have thought that a maximum of elastic modulus would have corresponded to a maximum of the ratio. If the structure has reached its equilibrium, its final equilibrium, the shape of the drop should stay the same. So we can suppose that at this point, we are far from the Laplacian profile, and maybe the elastic modulus is wrong. So to get a better idea, we change the frequency of this oscillation to evaluate the behavior after the maximum. On this slide, the frequency changed from 0.05 to 0.2 Hz. Before analyzing the global behavior of the moduli and the volume area ratio, let's have a quick look on the drop shape, depending on the frequency. Higher frequency shows membrane deformation, wrinkles, and even breaks at the interface, whereas it's not the case for the low frequency. Now, we can say that this decreasing slope is affected by the frequency of the oscillation. So the conclusion is simple. Here, the elastic modulus is 1. On the contrary, the R evolution is not dynamically affected by the frequency. The profile is quite the same, but only the final values are lower for the lower frequencies. Therefore, we can say that these parameters allow us to identify the deviation from the Laplacian profile, and especially if we follow its evolution here, we can determine what frequency allows to obey the limitation condition for elasticity evaluation with the drop-shaped tensiometer. Different interesting points for this conclusion. This ratio is a simple geometric parameter which gives fast and complementary information about the interfacial properties and the deviation from the Young-Laplace profile. It is easy to differentiate simple and solid-like interfaces because this parameter is sensitive to spherical and elongated droplets. But as we need to exactly determine the volume and the area of the droplet, it is sensitive to axis symmetry and especially to the presence of wrinkle at the interface. Further investigation are needed to identify a possible critical value of the ratio for interfacial transition. This will be done by changing the concentration of the surfactant and following the evolution of the R parameter. Thank you. I hope you liked the journey about complex interfaces and drop-shape rheology. Please contact me before and after the conference. I'm waiting for your question, and even if it wasn't possible for you to come and to visit Rio de Janeiro, it's always possible to find a part of Brazil in droplets. Ciao.